Okay, now we learned that how a transistor works and basically how do we model it when we have normal voltages and currents. But we started all of our discussions in this chapter with the promise that I can use this transistor, this device, as an amplifier, right? So let's actually make that amplifier, because in the beginning of this chapter, if you go back to the last week's notes, you will see that I claim that if I have a voltage controlled current source, I'm going to have an amplifier, right? We saw the equations and we saw that if the relationship between the relationship that governs the voltage dependent current source has a K that is large enough, we're going to get an amplifier. We're going to amplify the signal with the meaning that if I provide a signal with a certain amplitude to it, it is going to give me a linearly magnified version of that signal with a pre-specified gain or pre-specified ratio, right? So let's see that if I can actually make that amplifier using my transistor, right? So as a first step, let's consider this circuit, right? We're going to make an observation about how this circuit works as an amplifier. We're going to compare it to the circuit that is shown in the bottom, and then we're going to make some very important conclusions out of this observation. Okay, let's say that this transistor that I have, let's call it Q1. The emitter is connected to ground. The base or the collector is actually connected to some resistor. Let's call that resistor R load. And I'm going to define the output of my circuit as the voltage across this resistor, right? So let's say that this is my V out. Okay, what is the input? Well, the input is really coming from here. Let's say that this voltage source here is input, right? To give it a more practical real world kind of a feeling, let's say that this signal source that I have here is a microphone, right? So, and this microphone is generating a certain signal for me that, for example, if there's no sound, it's going to generate 0 volts or 0 millivolts. And if I have any kind of a sound, depending on the magnitude of the sound, it's going to generate some like signal that is up to, I don't know, 10 millivolts. Okay, so from 0 to 10 millivolts. Depending on the magnitude of the sound that is played into the microphone, I'm going to get 0 to 10 millivolts of signal out of it, right? Meaning that like I'm going to get the voltage that appears at this node, at the base of my transistor, is going to be somewhere between 0 to 10 millivolts, depending on what is the volume of the sound. And I've decided that this 10 millivolts maximum is not enough for me. I want the maximum to be 100 millivolts, meaning that I want to amplify this signal. Therefore, I would say that my V out, I like my V out to be between 0 to 100 millivolts, right? So I want the gain of this transistor to be 10, right? So required voltage gain is equal to 10, right? So meaning that if the microphone generates a 3 millivolt signal for me, I would like the output to have a 30 millivolts. And if it's 4 millivolts, then 40 millivolts. You get the idea, right? Let's say that we said that whatever transistor that we need to work with, we need to at least know the IS and beta, right? So let's say IS is 5 times 10 to the negative 16. And beta, well, in this example, beta is not going to be really important for us, but let's say it's 100. Okay? And the question is really asking me that what kind of a resistor, what kind of RL I should put there to get this gain of 10 or to get 100 millivolts output across the RL when my input is 10 millivolts, for example. Okay, let's go ahead and start the analysis. I would say the first thing that I need to observe, or I can actually see in this circuit, is that my V out is really the voltage across the RL. So it's going to be RL times IC. Good. Now, this RL times IC is going to be, I know that I can use my, I'm going to assume that my transistor is in the active mode. So I'm going to use the exponential relationship between the collector current and the base emitter voltage. So I'm going to say that my Vout is going to be RL times IS times exponential of VBE over VT. And then just to be very precise, remember from diodes that we had a -1 here. We have the same thing for transistors as well. So since I want to be very precise here, I'm going to put that -1. For most cases, when VB is much greater than VT, you can kind of ignore that -1. But in this case, because I know that my base emitter voltage is just the voltage of the microphone, which is around, well, somewhere between 0 to 10 millivolts, and my VT is 26 millivolts, I cannot really ignore that because VB is not much greater than VT, right? Okay, so if I have this expression, then I can say that my Vout is equal to RL times 5 times 10 to the -16 exponential of, let's say my Vin is at its maximum, so 10 millivolts over 26 millivolts, that is the VT. And then there's a -1. Okay, so this is the argument of exponential, by the way. Let me do the same thing here. Okay, now if I calculate this, I'm going to get this is equal to 2.35 times 10 to the -16 RL. Okay, so basically all of these numbers multiplied by each other, you get 2.35 times 10 to the -16. So now, because my input is 10 millivolts and I want to have a gain of 10, therefore my output Vout has to be 100 millivolts, right? So for this expression here to be equal to 100 millivolts, I need to actually figure out what should be the RL, right? So this should be equal to 100 millivolts at the output. Therefore, I can say that RL has to be 4.25 times 10 to 16 ohms. Okay, so if I choose this RL, I'm going to get my signal amplified with a gain of 10. Everything is nice and good, and I can actually get a gain of 10. It's a good amplifier, right? What is wrong with it? I'm hoping that there's something that is bothering you with my solution, or like with the result that we got, right? If you look at this resistor, it's extremely large. This is something we can never have on chip or off chip, right? As an integrated circuit or just a discrete resistor, right? The kind of resistors that we're okay with are basically tens to hundreds, or not, like maybe a few kilo ohms or, well, tens of kilo ohms, right? This is 10 to the -9 is a giga ohm. So this is 10 to the -6, 10 to 9 is the giga ohm. So 10 to 16 is like 10 million giga ohms. So that's absolutely impossible to be implemented, at least for the cases that we care about, right? Anything above a giga ohm is, well, or tera ohm are basically really hard to actually implement them precisely, let alone tens of millions of giga ohms, right? Even if it is implemented, it's going to be gigantic. So like imagine that you want all of these circuits, and this is a little amplifier, right? You want to have, if you remember from lecture 1, I mentioned that in an integrated circuit, you might have, I don't know, billions of transistors. And if one single transistor, single resistor amplifier is going to have such a large resistor that could be as big as, I don't know, if you implement it on chip, on silicon, it might actually take as much area on silicon that like a billion transistor will take. So it's definitely not a good idea to do this. So this is something that we cannot have, right? So what should we do? Like I want an amplifier with a gain of 10, and it looks like that with this transistor, which has a normal IS and normal beta, I end up having a huge and gigantic resistor. There should be something wrong there, okay? I'm going to repeat this experiment, but this time I'm going to make a small change in my circuit and see a very interesting thing that happens. So this time I'm going to have the same RL. I'm going to define my Vout the same way. So positive, negative V out. Okay, and the same V in, the same microphone, except this time I'm going to add a battery here. So this is really a battery. Okay, and let's say that battery is 0.75 volts. Okay, and I'm going to feed that to my transistor and see what happens and see what kind of resistor do I need to actually have here, right? Just to imagine what kind of, in time domain, what kind of a voltage I'm having at the base of the transistor. If I plot that, it's kind of having, I have two voltage sources in series here, right? One DC voltage source, the battery, and then there is the microphone on top of that. So you can imagine that if I plot the voltage at, so let's call this VB. If I plot this VB versus time, I know that it's going to have a DC value of 750 millivolts. And then on top of that, depending on what kind of voice you're going to have, like somebody is going to talk to this microphone, so depending on the volume of their voice, we're going to get basically different magnitudes, but those different magnitudes are somewhere between 0 to 10 millivolts. So if the base is 750 millivolts, you're going to go up from here, depending on the sound that you have, up to 10 millivolts from here. So the upper level is 760 millivolts. So again, my signal is actually varying by 10 millivolts, but then instead of varying between 0 and 10, I am actually adding a battery here. Therefore, I'm having my signal changing between 750 millivolts and 760 millivolts, right? Now let's actually do the calculation again, right? This time I'm going to write, well, V out is the same story, it has the same equation. So it is RL times IC. So it's going to be RL times the IS that I had, so 5 times 10 to the negative 16. And then exponential of, well, this time instead of 10 millivolts, I'm going to put in, once I'm going to put 750 millivolts over 26 minus 1. And the other time, I'm going to do the same thing, but with 760 millivolts. I want to know how much current will change, right? So maybe instead of writing V out expression, let's just write the IC expression. So I know that IC1 is equal to, so for V in, not V in, for V base. For V base equal to 750 millivolts, I'm going to have a collector current that if I do the math, I'm going to get a number equal to 1.7 milliamperes. Great. Now for VB2 equal to 760 millivolts, I'm going to have IC2. And I'm not going to just write, well, let's just write the equation. Again, it's not going to take a long time. Exponential of 760 millivolts over 26 millivolts minus 1. And if you do the math, you're going to get 2.48 milliamps. Okay. Now, by the way, if I wanted to do the same thing for the previous circuit, for the 10 millivolts, we got the IC that was around, that was exactly this number. So 2.35 times 10 to the negative 16 amperes. And for if the VB was 0, you would just get a 0, right? So I hope that that's obvious. So if VBE was 0, then e to the power of 0 would have been 1. 1 minus 1 would have been 0. Therefore, your current would have been 0. So if we were changing between 0 and this current, now we're changing the current of the collector is changing between 1.7 milliamp and 2.48 milliamps. Okay, good. So now I know that when I have a 10 millivolt input, I'm going to get this current at the output, right, for the 760 millivolts. Therefore, now I know that when V in changes by 10 millivolts, my V out, that is equal to RL times IC changes by, so for 750 and for 760, right? So for 750, my V out is going to be, well, we don't actually have to calculate the two numbers. I'm going to say that this is basically, I want to say that V out is actually, I want V out to change by 100 millivolts when V in is changing by 10 millivolts. So I know that when V in changes by 10 millivolts, my IC changes by 2.48 minus 1.7 milliamp, right? So it's going to be equal to 780 microamp or 0.78 milliamp, right? So when input changes by 10 millivolts, my IC changes by 780 microamp. And to just put this into perspective, in the circuit on the top, when my input changed by 10 millivolts, my current, the IC, changed only by 2.35 times 10 to the negative 16, right? Here, my IC is changing by 780 microamp, right? Now, how much RL do I want to get the V out of 100 millivolts? Well, I just need to do a division. So therefore, the RL that I want is going to be the 100 millivolts at the output over the change in the IC, so 780 microamperes. If you do the math, you're going to get 128 ohms. And that's a resistor that I can definitely implement on the chip, or I can buy from any store and use it, like basically put together an off-chip kind of a discrete electronic circuit for myself. This is a reasonable resistor. It's only 128 ohms, okay? Compare that to like tens of millions of gigohms. So it looks like that if you step back and see what happened, in the first circuit, I only had the signal connected to the base. So I had a small variations at my base voltage. And I saw that those small variations cause very small current changes at my collector, right? My current, when the V in was 0, my current was 0. When the V in was maximum, my current became 2.35 times to the 10 to the negative 16, right? Therefore, to get to a voltage variation that is as big as 100 millivolts, I actually had to have a gigantic resistor connected to my collector, right? However, for the second circuit, I added this battery and I had the same microphone that basically converted my voice into a voltage that changes from 0 to 10 millivolts. All I did was I added that I added a battery in series with that microphone so that the voltage that appears at the base of my transistor changes, instead of 0 to 10 millivolts, my voltage is changing from 750 to 760. Now, to see that how much variation do I get at the current, I looked at what kind of current 750 millivolts gives me. This was the current. And then I looked at what kind of current the 760 millivolts gives me. And this was the current, right? And then based on this, I realized that when I have zero sound, this is the current that I get. And when I have the maximum sound at my microphone, this is the current that I get. So the voltage variations at my base is going to cause a current variation from 1.7 to 2.48. So the range of current variation is going to be 780 microamperes. Okay, and therefore, because I want 100 millivolts voltage variation at the output, therefore I need to have an RL that basically, when it's multiplied by 780 microamp, it gives me 100 millivolts. And I found that RL to be 128 ohms. Now, if I want to see or basically visualize all these discussions on the plot that I'm familiar with, which is the IC versus VBE plot, I would say that for the first circuit, I was actually operating at this region, right? My VBE was changing from 0, which is here, to, let's say here, 10 millivolts. Okay, and you can see that when I'm changing in that range, you can see because of the slope of this exponential, which is pretty flat at that point, my current changes by a very small amount. And indeed, the numerical value of that change is here, right? It's 10 to the power of negative 16 amperes in that order. However, by adding the battery, what I did is that I kind of moved my operating point to somewhere around here, let's say. So this was 750 millivolts, and let's say here is 760 millivolts. Now, if I look at how much current change it's going to cause, I can see that in terms of current, my IC is actually changing by a lot, simply because the slope of my exponential at this point of my curve is actually much greater than the slope at the very beginning, close to the origin, right? So here I had 1.7, and here I had 2.48 milliamps, right? And that is really what I did. That is really the, if you want to like visualize this, this is what is happening. This is why we got so much different kind of results for my for the resistor that I need to have in my circuit.